equipotential surfaces. Potential means it always refers to a point. Potential at a point. It arises as a result of electrostatic charge. The charge may be positive or negative charge, or it may be a type like this point charge. Point charge. The charges only at the point. And the charges may be a linear charge or surface charge. And the charges may be an electric dipole like this. So this potential is all because of the electric charges in that space. Let me define in brief the potential at a point with respect to a point charge like this. I have taken a positive charge and the amount of charge is q and the point is here. It is the direction of electric field. The point here at this point, what is the definition? How do you define the electric potential? At this point, if you place a unit positive charge, it means a charge of 1 coulomb, that is unit charge, and should be positive charge. It is, this is positive, this is positive. Due to same type of charge, there is electrostatic repulsion. So this electrostatic repulsion will push this point, unit positive charge, away from the electric field. That is in the direction of electric field. And finally, it drives out of the electric field, that is at the infinite point, at which the point experiences no electric field of this charge. That is called infinite point. While doing so, some amount of work, that is moving a charge, work is done. So work is done by the charge. Here the work is done by the charge because the charge is moving by itself, spontaneous. Work is done by the charge. That amount of work done when the point is moving from this point to this point is called as potential. In other words, at this point, the point is that some amount of potential energy is stored up. It has now changed into work. That is completely, that is changing to work to what is that? To kick the point from here to here. That is also called as potential. That is a conversion of potential energy into work. That is the way. In the other alternate fashion, what is the definition? The same point here at infinity. We can move the point from this to the initial point, initial state. For this, work we have to do on the charge. So work is done on the charge because this point charge cannot move against the electric field, repulsion. You have to do the work. Work is done on the charge to move. Work is done against the electric field. So what amount of work it is needed to move the point, that is point charge from here to here, it is called as potential, or the amount of work or energy is completely what is that converted into potential energy when it is the point come from here to here and stores up as a potential energy at this point. That is called as potential. Other way, that is mathematical definition. So potential at any point is amount of work done to move that positive unit positive charge from infinity to that point. That is unit positive charge. So amount of work done to move the unit positive charge from the infinity to that point is called as potential. That work or energy, that is there is energy in the form of different forms, either in the form of what is that work or potential energy, kinetic energy. So it is just a transformation of work into potential energy. That energy is called as potential at the point. Of course, in the space, different points have different potentials. That is the definition of potential. And the mathematical definition or equation for a potential at a point is given by this. V is equal to K into Q into R, Q divided by R. The same equation we have derived it in some previous class. What is Q? Amount of charge, magnitude of charge. What is K? Coulomb's constant. That is 1 over 1 divided by 1 upon 4 pi epsilon naught. And R is a distance between the point and this point charge. It depends on the potential, depends on the amount of charge and inversely on the distance between the point charge and the point where the potential is defined. Distance separation. So this is regarding the definition of the potential. Meaning of equipotential surfaces. What is meant by equipotential surfaces? It is a surface on which every point has same potential. That is surface. Every point on the surface, you take any point on the surface, the same potential, no difference. The surface may be of any kind, any shape. It may be 2-dimensional or 3-dimensional. But the entire surface, where any point in the surface, the potential is constant. And equi means same potential. It is called as equipotential surfaces. So about this electrostatic charges, maybe a point charge or linear charge or an electric dipole like this or electric field like uniform electric field like this. How these equipotential surfaces arises? What is the imagination? How do you imagine the surfaces about these charges? What are the possibilities? What are the possible surfaces about these charges? So let us see that if the point that is charge is point charge, if electrostatic charge is point charge like this. This is of course a positive charge or negative charge, doesn't matter. I have taken here a positive charge. About this point, we can draw one spherical surface, that is a sphere, the allosphere, with a surface, not a line circle like this. It is just like looking at a circle, but it is a sphere. A spherical surface, 3-dimensional spherical surface about this point as a center of point. And this is the radius of the sphere. And I see that, observe, you take any point after this drawing this diagram, spherical surface about this center, you take any point on the surface, any point on the surface. All points have same distance from center of the distance from this point of center point, and that is r distance. So that is Q remains same, this amount of rise. If R remains same, because the points are different places, different directions, suppose now, but the same surface. So if that is so, what is that? Look at that, potential is equal to, depends on only these two factors, mainly is constant. This remains constant for the center, and all the points are the same mark, therefore the potential remains same. What does it mean? There is surface symmetrical. What is spherical? Spherical shaped surface on which the points are taken. Any point you take, any point on the spherical surface, the potential remains same. Therefore, this surface, this shape of surface, spherical shape of surface is called as equipotential surface with respect to point charge. So this is the shape, or what is the design we can imagine about this positive charge, that is spherical surface, is called as equipotential surface. And about this point, we can draw many spherical surfaces like this. These spherical surfaces are concentric spherical surfaces. Concentric spherical surface means all surface, all circles or spheres have common, what is that, center, same center of point. They are called as concentric surfaces. Of course, the radius are different. If we say radius of this spherical surface is R1, radius of this is R2, radius of this is R3, like this, R1, R2, R3, radii of sphericals. Radii means plural. Different spherical. You can make numerous spherical surfaces. What is the difference here? Like this now, every point on the surface, same potential. Every point on the surface, same potential. Circle is bigger, that is scale is bigger. Every point on the surface, same potential. Scale is bigger, radius. But look at the here, these surfaces have not same potential. This potential is, what is that? Usually higher potential. Distance is smaller. This potential is, what is that? Higher value because higher radius away from this. So it depends on what is that, is inversely related to radius of the sphere. Higher, what is that? Higher value, lower potential. So likewise, this is 60 watt, it will be 40 like this, it is 20 like this. So each surface has its own, what is that, value of potential, that is a equipotential surface, but different surfaces are different potential. So all these surfaces are called as equipotential surfaces. About these point charges, we can have number of concentric sphericals, so number of equipotential surfaces like this. Their potentials are given by this. Only difference is the radius difference. That is equipotential surfaces about this point charge. Similarly, what is the equipotential about this? What is our linear charge? What is the linear charge means? The charges are distributed in linear shape, continuous distribution of charge. This charge, amount of charge, let us say is Q, plus or minus, I have taken here plus, and the length of the line is L. So, what is the possibility of this surface? That is equipotential surface about this linear charge. Now we can draw, what is that? A cylindrical surface about this. So if you draw a cylindrical surface about this line as an axis of cylinder, that is linear charge as axis of cylinder. You can take this linear charge as axis of cylinder. About this axis, if you draw a cylinder, a cylindrical surface like this, and observe every point on the cylinder, that is the radius of the cylinder is equal to r. Distance between the axis and the surface is r. It is same all around, every point. So look at the point, every point has same distance from this line. every point the same distance from the line. This is linear charge. So total amount of charge is plus q. And recall, we have derived that is mathematical equation for, that is, electric field at this point, any point is this one 2k lambda by r. 2k lambda by r. What is k? Coulomb's constant. What is r? Radius of the cylinder. Distance of any point on the surface from this line r. Lambda is, that is, charge density, linear charge density. Linear charge density is amount of q divided by total length of the charge. So that is the definition for what is that field on the surface of the cylinder. But I need what is the expression for potential on the surface, any point on the surface. So potential is equal to ER. So potential at any point is equal to ER definition. Recall that. E into R. So E into R means this into R is 2k lambda. That is potential at any point on the surface is equal to 2k lambda. So that the potential is constant, 2 is constant, A is constant, lambda is constant about this linear charge. At any point, what is that? It will like that. So look at that. If you estimate potential, it is same. Surface, no? There is large surface area. You take any point on all the entire surface, all points in the surface, same potential. Therefore, this surface becomes a equipotential surface about this linear charge. That is a potential. So that is a design or the shape of the surface. This surface is called as equipotential about this linear charge. This is the way of drawing the equipotential about this linear charge. In the same way, we can have what is the number of cylindrical surfaces, concentric cylindric surfaces. Concentric cylindric surfaces. What is concentric means? Same axis, yeah, as a linear charge. One cylinder, one more cylinder, a difference, one more cylinder, only radius of cylinder difference. So radius, higher radius, one more radius. You have surfaces, no? Becomes larger and large surface. Each surface is equipotential surface, cylindrical surface. This is also equipotential surface, but the potential is different. Here, higher potential, lower potential. Potential decreases in the direction of electric field. This is the direction of electric field. Electric field perpendicular to the surface. This is of course amount of charge. Of course, R1, R2 are the radii of the cylinders. So likewise, we have what is that about this linear charge. We can have what is that number of cylindrical surfaces, number of concentric cylindrical surfaces, same shape, different sizes. So these surfaces are called as equipotential surfaces about this linear charge. Now, what is the type of or the surfaces we can what is that? Imagine in uniform electric field. What is uniform electric field? Uniform electric means a series of what is that? Parallel lines at equidistance. A representation of uniform electric field. A series of what is that? Parallel lines at equidistance with direction like this is called uniform electric field. If there is a uniform electric field in the space like this, how do you imagine those equipotential surfaces? What type of the surfaces we imagine in this electric field? That is, if you draw what is that? A plane, perpendicular planes, say planes, of course a rectangular plane like this or any kind of planes, what is that? A plane like this, perpendicular planes perpendicular to the electric field like this. A plane perpendicular to exactly perpendicular to the electric field. A plane perpendicular to electric field like this. So look at on the surface. On the surface you have different points. So electric lines are passing through, but at this, that is on plane, any point, just consider any point. Look at the every point on the plane. Every point, what is that? Same type of, what is that? Electric lines passing through. Same type of electric line passing through. Therefore, electric potential must be same. Just observe any point on the surface. There are a number of points you can draw on the surface like this. That is, a surface is perpendicular to this. So at every point, same line of electric line pass through. Therefore, same potential. So this plane is called as equipotential surface. This is also equipotential surface. Depends here what is that? Of course, the potential decreases. From year to year, potential decreases because potential decreases in the direction of electric field. That is the electric field, what is that here? Is away. So in the direction, the electric field decreases. Therefore, potential you see what is that? That is equipotential surfaces, equipotential surfaces, equipotential surface. But difference with what is that? Difference is always there between the potential. That is potential difference between the two planes. So this is how we can visualize, or what is that? Imagine the equipotential surfaces in uniform electric field. The drawing of equipotential surfaces in uniform electric field. In electric dipole, what is the imagination of a plane like that? Electric dipole, just recall. So, any point, just recall the general mathematical equation for electric potential at any point around the dipole. Electric potential at any point around the dipole, it is V is equal to Kp into cos theta by r square. Any point around the general equation. Kp into cos theta is derived in some class, some previous class. Just recall it. K is Coulomb's constant, P is dipole moment of this dipole. Dipole moment of this dipole. And theta is the angle between the point and the center of dipole. Angle between the point and the center of dipole. That is it. That is R is the distance between the point and the center of dipole, and angle is the angle between the line drawn between this point and the point where the potential is estimated on this line dipole. It is a angle theta. So Kp cos theta r square is the potential around, that is potential at any point around this dipole. So let us write the possibilities already derived in the previous class. If we take the point along the line, axis line here, when the point is along the line axis, that is theta is equal to 0, cos 0 is equal to 1. So along the line, potential is Kp by r square. It is derived from the previous class. Along the equatorial line, what is that? This point, what is that? Here, the line and this is 90 degree. Line joining this point and the midpoint and this line is 90 degree. If that is 90, cos 90 is equal to 0. So this becomes 0. That means at any point on the vertical line, potential is 0. That is one vertical line exactly passing through this point. So likewise, not only one vertical line, we can able to draw any number of lines. This is in all different directions. It has same line, no, but it is the same line. This is in one direction, in different directions, in all possible, 180 degree, in all possible directions, you can draw lines on a plane like this. So in this place, what is that? This is called as equipotential surface. The plane exactly passing through the center point is a bisector of dipole, plane bisector of dipole. And observe that every point on the plane, same potential. That is 0 potential. Every point on the plane is 0 potential. Potential is called as equipotential same potential may be 0 or some other value, doesn't matter. Doesn't matter. So it is called as equipotential surface. So this is a kind of equipotential surface we can imagine about this dipole. That is a drawing of this. So that is all. This is how. These are the different types of equipotential surfaces we can have about this electrostatic charges. Here electric field, electrostatic charge like this, electrostatic charge like this. So this is drawing of this meaning of equipotential surfaces and this geometrical drawing about the different electrostatic charges. Let us discuss in brief what are the properties of these equipotential surfaces. We are talking about different surfaces, but they have common properties. You take any surface, there is always a common properties. There is one property, delta V equals 0. I told you on the surface you take any point, same potential. If you take any 2 points, difference in potential is 0. Same potential, same potential difference is 0. That is delta V. A difference in potential between any 2 points is 0. That is delta V equals 0. That is one property. Potential difference between any 2 points is 0 on equipotential surface. That is one property. And one more property, since potential difference is 0, when the point is here, when you want to move a charge on the surface from one point to other point, work is done. Work is done by the charge or work is done on the charge, of course. So what is the amount of work done? Is there any work done for moving a charge from one point to other point? See that there is no work done because work done is equal to potential difference. What is potential difference from one point to other point? It is the amount of work done in bringing what is that, moving a unit positive charge from one point to other point. That is W. Since delta V equals 0, W equals 0. It means no work is done when a charge is moving. No work is done by a charge or no work is done on the charge. When the point is moving, when the charge is moving in the surface. There is another property. And one more property, direction of the, what is that? These, that is the field on the surface. Surface is a direction. That is surface, plane surface, or what is that, cylindrical surface or spherical surface. Surface as a direction and field as a direction. The surface direction becomes a dr, displacement. Why displacement? On the surface when the charge is moving, it is a displacement. Displacement is a direction. So certain direction and the surface directions are same. So any displacement on the surface, that is the direction. So the direction is same as the surface direction. That is on the surface like this, a rectangular surface, that is direction of the surface, that is direction of the electric field. They are always what is that, perpendicular to each other. Direction of the electric field is always perpendicular to surface of the equipotential surface. Proof. That is mathematical proof. So when you learn what is that, recall this equation definition. So electric field is a rate of change of potential with R on the surface, that is minus, decreases away from R from the charge. So rate of decrease of potential with the distance away from the charge, that is E. It is rewritten as this is as E. dV is equal to minus here. So dV I said already is 0. 0 is equal to this into this. So this is what is that? That is, these two are vector, this is scalar. Therefore, it is a dot product. Definition for dot product is this. Cos theta. What is theta? Angle between these two directions. Already said 0. That means 0 means For this equation, mathematical equation to be 0, that is theta must be 90 degree. That is cos 0 is 0. Cos 0, cos 90 means 0. So theta must be 0. Theta must be 90 degree. 90 means the angle between this direction and this direction is 90 degree. Therefore, this is how we can prove that direction between this and this is 90 degree. This is direction. Suppose the surface is spherical surface like this. So here there is surface and this is electric field. So that is what is that? This is a 90 degree between the surface, point of surface and this electric field. Either this direction or this is another same. Suppose the surface is cylindrical surface like this. That is what is that? Perpendicular, that is surface. This point is surface at which you see the interaction. The surface is in perpendicular direction to electric field. Any direction like this. So these are the properties, important properties of what is the equipotential surfaces. When you talk about equipotential surfaces, it should satisfy all these things. That is delta V equals 0 and work is 0 for a movement of charge on the surface. And the direction between electric field on the surface is always vertical 90 degree. So this is regarding the discussion about the equipotential surfaces. What are them, how the shape and what are the properties. This let us finish up.